Now let's take one more look at distortionless transmission. So in our distortionless transmission, we had an input signal and an output signal. We're trying to figure out some way of putting in an input message xt, and we're trying to get this output message y of t, where the only changes that we're going to allow are some constant that's multiplicative, and some delay in time that's associated, right, with how much time it takes to pass through all of our communication system. And in the previous video, we determined that this is the form of the transfer function that is allowed in order to have this distortionless output. So if we were to do this, if we were to build this transfer function, and we were to analyze it, we'll look at it on the frequency domain. So in the x-axis, this is frequency, and then in y, we have both the amplitude, which has some k. So our amplitude response is constant. So no matter what the frequency is, right, we have a constant amplitude response. So if you have let's think about a song that has bass notes and treble notes. We'd have some bass notes. Those would be multiplied by the same constant, and we're transmitting it, and these treble notes also are being multiplied by the same constant. Now, what about the phase? Well, we are saying that it has a constant time delay, and this constant time delay, we know it's constant because the slope of our phase response, so our phase response, the slope of it is constant, which means it's linear. So we have this linear phase response. And we also have this other term, which is right here. So when frequency is 0 hertz, we also see that the phase response is 0. So this indicates to us that we have a distortionless transmission, that we've fulfilled this obligation, right? So the constant is the time delay, the slope of this is the time delay, and the magnitude amplitude response is also constant. So taking a closer look at the phase response, we determine that the ideal phase response would be minus 2 pi f td, and we determine that using some of the Fourier transform properties, the time shifting property. And so we know that the slope of this is minus 2 pi d, right? And we found that because we just took the derivative of this, right? So if we take the derivative of our phase response, we would be able to find the slope of this line that describes the phase response. We'd be able to find that slope as being minus 2 pi td. And of course, these are constant, and so is the time delay. So what this means is that no matter what the frequency is, we have the same time delay. So if you're right here, we're transmitting these bass notes, right? They have the same time delay. So the slope right here is constant. And then if we go up here and we look at some treble notes and we look at the slope of our phase response, we see that the slope is still the same. So what this tells us is that the time delay for these bass notes is the same as the time delay for our treble notes. And that's great. This means that the entire message, no matter where it is in frequency, is going to contain the same time delay for all the frequencies. So what happens though if you have a change in the slope on that phase response? So let's imagine that we have a change in the slope of this. And let's further imagine that the amplitude response of this transfer function is 1. So this is an all pass. So when we take our song or message into a system, right, we take it into the system, and what comes out is all pass, meaning that k, that multiplicative constant, was equal to 1. So there's no actual amplitude distortion at all. The xt in amplitude is the same as that yt out amplitude. But what has changed is our phase response. And so let's see that this all pass systems are not necessarily distortionless. So if we have this all pass system where we have a phase response where there's this kind of bend or kink or twist in the phase response at some frequency f naught, we can see that there is one slope at one frequency, and then here, right at that F naught, we have a different slope. So what does that mean? This means that the slope below this frequency has some time delay, minus 2 pi time delay 1, whereas the slope above our frequency F naught has a time delay of TD2. So we have created a new situation with a phase response that has a twist in it. And that twist means that we have two slopes, which now accounts for two time delays, which is quite bad because this is really what distortion is. So this is a time-based distortion in the phase response. So what this means in real life is that if you have some base information, so this is a song, let's say again, we're sending the base information, and the base information has one time delay. But then you go up here, and this is your treble information. The treble parts of the song now have some second time delay. And so if you have a big difference, if time delay 1 and time delay 2 are quite big, say 1 second, then this song is going to be indistinguishable at the output, right? Because you've passed it through a system where the bass and the treble are being delayed by 1 whole second of difference in the upper treble frequencies and the lower bass frequencies. And so this would be a pretty serious case of distortion. We can characterize the distortion in the general case where we have the phase response looks like this, and the time delay in their phase response could be a function of the frequency. So it doesn't have to be quite as extreme as this, right? It could be a gentle change, but it's still some change in the time delay across your frequencies. And we can write here in the general case that our time delay as a function of frequency is going to be related to the derivative of the phase response. And we'll see how this is important as we look to the future and try to determine how can we make distortionless communication channels, even if they're all pass, or how can we find a set of frequencies or part of a frequency range that might minimize distortion in our channel.